I think that I am not going to follow literally lecture 1, 2, 3, 4 from now on. What I may do is skip on some topics later on and that way fill in. So anyway, I just wanted to say in case you are following from your notes. So we were talking about I think I had that already on the screen. So we wrote the Hugoniot and the Rankine and the Rayleigh line in dimensionless form, and we said that then these two equations for a given mu, namely a given mass flux, determine the final state of after the wave have propagated. So what is usually done is just you plot these two relation, pressure versus specific volume or reciprocal of density, and the intersection is clearly the possible solutions. So before we do this, let's see one at a time what they are. So first of all, here are the Hugoniot. Okay, the relation is written here. And the Hugoniot turn out to be hyperbolas that asymptote here to this line and to this line, which I will write explicitly in one of the next transparency. But note that for different Q, different heat release, it's displaced from to the right and up. When Q equal to 0, which is this curve here, it's the only curve that goes through the initial state, right? Because the initial state corresponds to P equal to 1, V equal to 1. So P equal to 1, V equal to 1 is satisfied only by this expression when Q equal to 0. Any other Q does not, so it's displaced. Okay, so these are the Hugoniot. The next thing is here are the asymptotes. When P goes to infinity, which is this dotted line here, V goes to this value. In other words, V can never be less than this value because clearly P cannot go more than infinity. Similarly, there is an asymptote here, which is when V goes to infinity, but this asymptote is below the axis, so clearly it's not possible beyond this point because then P become negative and it's not physical. So the solution must be, first of all, restricted to that range, okay? The second thing, it's not quite obvious maybe a priori what these curves are, but they are really hyperbolas when you shift the axis to the two dotted straight line. In other words, it's a hyperbola got shifted from the axis. It's an actual hyperbola, or rectangular hyperbola, as we call it. Okay, the next thing to note is that the Rayleigh line, which are written here, right, for different value of mu, since mu must be positive, mu is the mass flux in dimensionless form, it tells you that this is a straight line with a negative slope, right? P versus V has a negative slope. So the only possibility of the Rayleigh line is that these green lines, right? They cannot go on they cannot have a positive slope. They can only go like this or like that, okay? Okay, and clearly from this picture also you can see that they can cut more than once the Hugoniot, but we are going to talk about that in a few minutes. So there is a range of, there is a limit of where the solution could be, and they could be only in this rectangular area or this rectangular area. They cannot be here because the Rayleigh line cannot be positive, right? Has a negative slope. So they are restricted to here and here. The solutions that correspond to here will be known as deflagration. They correspond to, just because of their properties, the pressure changes relatively slightly, it decreases. And the solution in this area will be known as detonation because the pressure increased tremendously. The name detonation, deflagration, of course, depend on the properties that we're going to discuss in a minute. So this is the discussion of the Hugoniot and the Rayleigh line. Now let's consider first the case Q equal to 0. Q equal to 0 means no heat release, right? So you have a wave, you have a gas that is propagating from to the left, or in this frame relative to the wave, it's stationary. And there is a change in pressure and density and so on across. So what could that correspond to? Well, one possibility is this solution. That's one intersection of the Rayleigh line with the Hugoniot. And that will correspond to a situation where downstream the velocity is lower, the density increases, and the pressure increases, so that's like a shock wave. Okay, so this is not like, but it's a shock wave. There is, of course, another mathematical solution which corresponds to this square blue region here, but that would correspond to a rarefaction wave, a wave where the density increases rather than, decreases. But then this is physically not possible. It just violates the second law of thermodynamics, and therefore that solution is not acceptable in pure gas dynamic situation, okay? No combustion. So I just brought up that as a reference. We are interested, of course, in solution where Q is positive. So note that the Hugoniot is displaced from, it doesn't go through the point 1,1, but the initial state is here, and the Rayleigh line can be, for example, this blue curve or this green straight line. So it can cut twice the Hugoniot, either above or below. And so you can have, if it's here, it's detonation. So the two solutions are known as weak detonation and strong detonation. And when it cuts on this side, it's weak deflagration and strong deflagration. Okay? Now, remember that the slope depends on the flow rate. And so clearly, this slope can decrease, but not below the purple line. In other words, the purple line is the lowest mu that you can have for a solution to exist. And that corresponds when the two solutions coalesce and are and the Rayleigh line is tangent to the Hugoniot. So when the Rayleigh line is tangent to the Hugoniot, you can only have one solution, and it's known as the Chapman-Jouguet. Okay, so this is the Chapman-Jouguet situation. It was discovered by Chapman and Jouguet independently in the 1800s, something like that. Similarly, you would have a situation here when you increase the flow rate or you increase mu, you cannot increase it beyond a certain value, and that would correspond to a situation where you will have a Chapman-Jouguet deflagration. So you can either have weak, strong detonation, weak, strong deflagration, or the Chapman-Jouguet. What's the difference between the two? It's basically summarized here. Try to keep in mind that picture, okay? Note that in the detonation case, you start with P equal to 1 and P increases. In the deflagration, P decreases. In the detonation, V decreases, so rho increases, and the opposite happens in the deflagration. So the detonation, there is a minimum value of mu, and as a consequence, a minimum mass flux, and therefore a minimum wave speed. Corresponding to the Chapman-Jouguet detonation. The Chapman-Jouguet would be the slowest. For mu bigger than mu Chapman-Jouguet, there are two solutions, the strong and weak. And in general, passing through a detonation, V is less than 1, so the gas slowed down. Remember that it's relative to the wave, okay? Then the gas is, rho is bigger than 1, the gas is compressed, and the pressure increases. In deflagration, there is a maximum value of mu, and therefore there is a maximum wave speed. and the maximum wave speed correspond to the Chapman-Jouguet deflagration. Otherwise, there are two solutions. A weak and a strong deflagration, and through a deflagration, the gas speeds up, the density, the gas expands, the density decreases, and the pressure decreases, okay? So it is the properties of these two waves that define what we call deflagration, what we call detonation. Now, the Chapman-Jouguet one, remember that one of the questions that we're trying to study here is, I posed it earlier, there are two questions of interest. First of all is to identify what's the final state, okay? Rho infinity, P infinity, or rho pt and v and so on. And the second question, what's the wave speed? Well, as we shall see, we cannot always determine from this analysis the wave speed, but we can always determine the final state. There is only one case that it's obvious that we can determine the wave speed, and this is the Chapman-Jouguet case. The reason for this is because in addition to the satisfying the equations, the Hugoniot and the Rankine and the Rayleigh line, you also have a tangency relation. That's an additional piece of information. And that tangency relation gives you an additional information from which you can determine the wave speed. So here is the Chapman-Jouguet wave. This is the Rayleigh line. This is the Hugoniot. It's the same expression that I had before on the transparency. If you take the derivative of the Hugoniot, dp dv, from here you get this relation. It requires, of course, some manipulation, but that's what you get. And dp dv from here, it's mu, but it's also p minus 1 over v minus 1. It's minus mu, but that. So this is the slope of the Rayleigh line. If you equate the two, you get an additional simplification that mu is equal to gamma p over v. Now remember, I show you that mu can be either related to the Mach number upstream or can be related to the Mach number downstream. This was one of the relation. So if gamma p over v is 1, it means mu equal to m infinity squared. And since, it means that m infinity squared is 1, right? Mu is that, so m infinity is 1. Which means that for the Chapman-Jouguet wave, the Mach number relative to the wave for both, I didn't distinguish here deflagration of the, so for both is sonic, is equal to 1, okay? Remember, it's relative to the wave. Okay. Once you have written that, once you have obtained this, you can also use this relation together with the Rayleigh line and the Hugoniot. In other words, now you have three equations, but you have three unknowns, but you can solve clearly for either P or V from this relation. And so if you, for example, try to solve for V, you get a quadratic equation. And the quadratic equation gives you for V the two possible values. The plus corresponds to the detonation, the minus for the deflagration. Remember, those are Chapman-Jouguet waves. So for Chapman-Jouguet waves, you can calculate everything: the pressure, the velocity, mu, and therefore the temperature, density, and so on if you need afterwards. Okay. In particular, you can also obtain what is the Mach speed, the Mach number ahead of the wave, which is the more important one because that represents the wave speed. And so what you find is that the two values are obtained here. So it implies that detonation are always m naught is bigger than 1, and so they are supersonic waves, and deflagrations are subsonic waves. So those are the two properties that characterize the two possible solutions. Moreover, it can be established again by playing with this relation that for strong detonation and weak deflagration, the Mach number behind the wave relative to the wave is subsonic, and for weak detonation and strong deflagration, Beyond the wave, the gas is supersonic, again, relative to the wave. It's convenient to think of, or to, this is another way to look at really what happened in a either detonation or a deflagration, but now I want to look at the particle velocity, okay? So U is the particle velocity. So remember that this was the configuration when an observer is moving with the wave, it's on the left. On the right, the wave is moving to the left, which was the lab configuration. So in the lab configuration, since the wave speed is minus v naught, and so v naught minus v naught, U is 0, right? So clearly the gas is quiescent, and on the burn side, U is V infinity minus V naught. Okay? Yes?
I'm sorry, did we ever define what the Mach number was?
I did in words, maybe I didn't write it. So the Mach number, I did in words when I was describing it, but the Mach number is essentially the velocity squared divided by the speed of, well, it doesn't have to be squared, it's the gas velocity divided by the speed of sound. So in one of my, let me actually run through this quickly. Yeah, so here is where I said it in words without, I missed really defining it, but essentially it's the gas velocity divided by the speed of sound. With a subscript 0, it means ahead of the flame, so this is the Mach number ahead of the flame, and with the infinity is behind the flame. Not the flame, but the wave. Yeah, good point. I'm glad that you raised that up. So, I want to look at this configuration. So you see, since V infinity remember V is the PV diagram that we plotted before, the deflagration was such that V is less than 1. V less than 1, it means V infinity is less than V naught, which means that U is negative for detonation, and U is positive, right, for deflagration, because the deflagration were on the right, where V infinity is bigger than V naught. What does this imply? Well, here is a picture of position as a function of time, and let's say this is the front, this is the wave front, okay? So let's say you have at time t equal to 0, you have a particle here which is far enough to the left. The wave didn't come to it yet, so it's at rest. It's not moving, okay? And then it's staying at the same position until it's hit by the wave, and then that particle starts moving following the wave if it's a detonation. Why following the wave? Because U is negative, okay? Or V infinity is less than A infinity. It will always follow the wave, but it will never catches it up because the wave is propagating much faster. Okay. For deflagration, here is the fluid particle. It is still at rest until the front hits it. And then you see, because U is going to be positive for deflagration, it's going to be moving away from the front. So the flame is moving to the left, and the burn gas is expanding and moving to the right. Okay, so that's another important distinction between the two. Okay, the few comments. The first one is that this so-called Rankine-Hugoniot analysis does not really determine the wave speed in general, except for the Chapman-Jouguet waves. And the second comment is we try to find, based on the conservation law, what are the relation between the state of the gas behind the wave relative to the state of the gas ahead of the wave. And we find some relation. But is it always is that enough to prove that such a change occur? Well, the change occur if the solution satisfies the differential equation, which is the conservation law. And so we have to ensure in general that there is a trajectory that moves from one equilibrium, which is on the left, to the other equilibrium, which is on the right. And furthermore, you have to ensure that these trajectories, or these two, are stable. In other words, that the solution, as a result of some small disturbances, does not never reach that equilibrium. So in other words, what I'm saying is, in general, when you have two equilibriums in some system, the fact that you found that these are equilibrium or possible steady state or possible equilibrium doesn't guarantee that if you start from here, you will necessarily end up here. You have to show really that there is such a trajectory that satisfies the governing equation or mathematically satisfies the conservation law. Okay. And the stability question depends on very much of the nature of these equilibrium. So for example, and now I'm not referring necessarily to neither deflagration or detonation. For example, if that equilibrium is a saddle, then the solution will try to get to it, but just run away, and so it's not a stable situation, so you will never be able to go from here to here. On the other hand, you can go from here to here, so that's in general what happened. Okay, so this is the, now this is a summary again of deflagration and detonation waves. So let's go quickly. The deflagration or expansion wave, they propagate subsonically. The burn gas expand, move away from the front. In a frame attached to the wave, the Chapman-Jouguet wave satisfy this condition. We have discussed that. Okay, here is an important result that I'm not proving, but just stating. The wave structure, which is something related to the existence of such trajectories, prohibits the existence of strong deflagration. So strong deflagration simply do not exist. And weak deflagration, it's what we call flames, okay? So in other words, there is no structure that connects the burn to the unburned state of a strong deflagration. On the other hand, there is a unique solution for weak deflagration, giving a definite wave speed for each gas mixture. This is the V naught that we didn't calculate yet, and clearly for flame is what is known as the laminar flame speed or the flame speed, and it is unique given the given mixture and given conditions. So, and that unique value cannot be determined from this simple analysis, but we have to go inside the structure and examine what is happening inside the flame structure, and we will discuss that probably tomorrow or later today. So deflagrations are nearly, and finally deflagrations are nearly isobaric. You notice that the pressure just decreases very slowly, and hitting the first intersection point, really the changes are quite small. And we are going to discuss this because it's related to the so-called zero Mach number approximation or low Mach number approximation that describe flames. And as a consequence, the density is approximately the inverse of the temperature. Okay, pressure don't change much. It can be treated as nearly as constant. Typically, deflagration or flames propagate at speed 10 to 100 centimeters per second. This is what the typical speed of, let's say, hydrocarbon, or the higher one, it's probably hydrogen air. And the purpose of deflagration is to produce heat, and that's what is mentioned here. Detonation, they are compression waves. They propagate supersonically. The wave retards the burn gas that is compressed and follow the wave, but at a slower speed. In a the Chapman-Jouguet condition were discussed already. You have the possibility of strong and weak detonation. A strong detonation can be produced by driving a piston at an appropriate speed, whereas the weak detonation, there is only one wave speed. In other words, you can produce strong detonation at any speed that you want, depending on how you really drive them. On the other hand, there is only one wave speed for which a weak detonation can propagate, but weak detonation are really seldom observed. And the self-sustained detonations, yes?
If a strong deflagration cannot occur, why do you say that it has a Mach number greater than 1?
No, I did not. I said that
On
on the previous one. No, I said a low Mach number.
Here in the notes, it says a strong deflagration
Oops.
has a Mach number greater than 1.
Oh, you mean on this one? Oh, well, you're right, but this is based on just the Chapman-Jouguet analysis. Those are the results that we obtained. And I later stated that among those, the strong deflagration doesn't exist. So that's true that this is mathematically correct, but it cannot be. So, I mean, it's a good point, but I think I mentioned that follow the first, and so, yeah, but that's absolutely right. I hope the question was clear. Was saying, why do you say that strong deflagration here have a m infinity bigger than 1 when they do not exist? That's true, they do not exist, but this is simply from the Chapman-Jouguet analysis. And they do not exist because no structure can relate from the initial state to the strong deflagration. Yeah, self-sustained detonation are the Chapman-Jouguet detonation. Detonations are typically rapid. They propagate like 3 kilometers per second. They are violent. The pressure increased tremendously, and there is a significant increase in temperature. And clearly, the purpose is not heating, but is more the strength, the destruction, and so on. Okay, what are we doing now in time? Okay, there are some additional comments that I have added here. Let me remember what they were. So the first is, in an unconfined obstacle-free system, the mode of propagation is generally controlled by the ignition condition. In other words, deflagration are initiated by a spark or a weak energy deposit. Detonation are usually provoked by shock waves or localized explosion, okay? Typically, I am not saying that this must be the case. The second comment that I made here is that deflagrations are weak subsonic waves. So the disturbance behind the wave can propagate ahead and affect the state of the unburned gas before arrival of the wave. In other words, they are essentially elliptic system of equation, and so the solution may depend on what is going on in all the boundary around, and so the real condition can affect the propagation itself. On the other hand, this is not the case in detonation because they are essentially supersonic and they just, the disturbance is just propagating forward. Expansion of the product can therefore cause a displacement of the reactant. This is related to the previous statement. And so you can have, of course, a wave that is propagate faster than the laminar flame speed, okay? And finally, due to, you can start with a flame or with a deflagration, and due to various instabilities, turbulence, obstacles, and so on, the flame or the deflagration can accelerate sufficiently and develop into a detonation, something which is known as DDT, or deflagration to detonation transition. and I will not, I mean, it's a very hot topic of research, and I will not discuss much of that. Okay. So I want to briefly, and I'm probably going to make this shorter than I had planned to, I want to briefly describe the structure of a planar detonation, which is known as the ZND structure, or Zeldovich-von Neumann-Doering structure. It was discovered nearly at the same time by these three people. And the idea is that the ZND structure is an inert shock that is followed by a fast flame or a fast deflagration. So I'm sorry that now the picture is we are moving to the right instead of to the left. So here is the deflagration is moving to the right, and the rest of this discussion will be in this direction. So we have, this is the detonation, say. It's moving at a speed. In the detonation literature, they usually denote the speed by d. So this signifies a fluid particle which is being compressed as it goes through, or as the shock goes through it, right? And then there is an induction, so the pressure increases tremendously through the shock. Similarly, the pressure and density. But then following the shock, there is a relatively a deflagration that occurs. So what happened is, like in a flame, you would have the temperature start to increase, and often there is an induction region. It takes a certain distance before it reaches, let's say, an ignition temperature, and then it reaches the maximum temperature, right? In this region, which is very similar to a deflagration, you expect that the density drop and the pressure drop, as it should in a deflagration. So this is typically the structure. Lambda is used very often as a progress variable in the detonation literature. So the progress variable could be, for example, the mass fraction of the product, which is 0 at the shock, and then 1 when there is complete burning, when everything is burned, right? So it goes from 0 to 1. Okay, so to describe this in the Rankine-Hugoniot analysis, this is what I will be doing in the next few transparencies. So now here is the PV diagram, and my initial state now is here. Remember, I want to focus on the detonation, so I'm not concerned about the rest of the diagram here, which is deflagration. So to emphasize this part, we have to change a little bit the scale. Okay, so the initial state is here. Lambda is 0, right? Remember, and that's the initial state. And the final state will be, if it's a strong detonation, is going to be here, or if it's a weak detonation, is going to be here. We're going to see in a minute that the ZND structure only describes strong detonation. It cannot be, there is no ZND structure for a weak detonation. So we're going to see that in a minute. But what I have drawn here is 3 Hugoniot. The one that correspond to lambda equal to 0, the one that go from the initial state, and then other Hugoniot in the middle, and then lambda equal to 1, which is the last Hugoniot, the Hugoniot where all the mixture is completely consumed. Now, clearly, the solution, the end state, must be on the curve lambda equal to 1, right? Just to remind you, here is the here is the picture. Lambda equal to 0, it's the initial state. Lambda equal to 1 is the final state. So all this is the structure that we want to see how it is described now in the Rankine-Hugoniot description. So the idea of the ZND is that you start, first of all, the mixture go through a shock. So if it goes through a shock, it must go through the Hugoniot that go through the initial state. Remember, that's the only Hugoniot that correspond to Q equal to 0, right? No heat release. So it goes through a shock, so it will follow this green arrow up to a point here, okay? Then, after this, beyond the shock, remember there is a deflagration where the pressure drops, the density drops. So that point must be above here. It cannot be here because you cannot then follow that with the structure that I described. So you must be at this point. This point is often called the Neumann point. And then you are going to drop, you're going to slide through different Hugoniot where lambda start increasing from 0 to 1. In other words, the mixture become more and more consumed, right? So it gets consumed here until the final state that you can reach, okay? And I think in the next slide I've shown how you can also reach the Chapman-Jouguet point, but clearly you cannot reach a point here on the as a weak detonation. So this structure is not possible for weak detonation, the ZND structure. Okay, so this is essentially the ZND structure, and it very much, well, because those are strong, right? Those are typically strong detonation, and I told you earlier that strong detonation are driven by a piston, and they can reach any velocity that you want. They are often known as overdriven detonation. And so they are, it is the piston that more or less determine for you the propagation speed of the detonation. Except in a situation where the detonation become unsupported by the piston, and then it runs at the speed, at the Chapman-Jouguet speed. So I think I am going to skip some of the rest thing. It's a little bit details. These are the, just few comments. The description of detonation usually assumes that diffusion effects are negligible. They are relatively small compared to convective effects, and so one focuses usually on the Euler equation. In other words, neglect viscosity and diffusion, and you see that this is the mass conservation, this is the momentum equation without the viscous term, and this is the energy equation. But here, of course, you have to account, of course, for the kinetic energy as well, but it's part of that. It's all expressed in this relation. Anyway, these are the equations that you typically solve, and the first thing is you can write what happened across the shock. Well, it's very easy. It's just it's very similar to the Rankine-Hugoniot relation that we wrote before with Q equal to 0. And then, so here are in fact the Rankine-Hugoniot relation. And then you are left with an equation that you have to solve that describe for you you see how lambda vary. The lambda dt is the only equation that describe the progress of the detonation within the structure from the shock until completion, and you can integrate this equation either numerically, or there are some approximate method to do it, and here are solutions you know, for the typical structure that I've shown you. Usually people draw the profile beyond the shock, but I have added here in red what you see, what the shock, what happened across the shock, just for completion of the picture. Okay, so, and this is just a couple of comments that typically planar detonation are unstable. They are not observed experimentally. and people typically observe the cellular or spinning detonation. They either spin in a tube as they propagate, or they are, you will observe multiple multi-dimensional structure that have this diamond shape that is known as cellular structure. It's not really very much my expertise, but I follow a little bit the literature on this, but not that much. And I didn't want to go too much into details here, but just to mention that as part of the discussion. There was another here, a couple of comments that I want to make about the failure of the detonation. If it's highly curved, eventually it fails. And this is the typical curves that you obtain. But okay, sorry, I'm going to cut short because I have quite a bit to fill in. Okay, so I have another 15 minutes before the next break. What I want to go quickly is through, from now on, we're going to only talk about flames or deflagrations. And what I want to discuss now is I want to scale the equation, write them in dimensionless form, and make few important comments that come from this. So the first thing is, just to remind you, we're going to always talk about a single-step reaction. Fuel plus oxidizer go to product, whatever the product are. Nu F, nu O are the stoichiometric coefficients. So those are a number of moles. And okay, so that's why okay, and the reaction rate, what I was going to say is that it's not the mass-based, but it's the mole-based. But very often, I will also use the symbol nu without subscript as standing for the ratio of the oxidizer to fuel stoichiometric coefficient, but this is the mass-based. In other words, gram per gram or kilogram per kilogram, whatever you have. Okay, so the reaction rate is going to be the concentration of the fuel, which is rho YF divided by the molecular weight of the fuel, raised to some NF, which is empirically known, right? The reaction order. The concentration of the oxidizer raised to NO, and the Arrhenius dependence on temperature. With a pre-exponential here, B T to the alpha, but I'm going to also neglect the small variation in temperature, and so assume that alpha is 0, so that's 1, and so you just have a B. So this is the form of the reaction order, and NF and O are known as the reaction order with respect to the fuel and the oxidizer, and the sum of the two is the overall reaction order, which is denoted by N. Okay, dimensionless equation. Well, really, dimensionless equation you can write only when you focus on a specific configuration. And the second thing about it is that it is really not unique. It depends on how you choose what to scale or what to choose as your characteristic velocity, length, and so on. Of course, if you are talking about flow of, say, water in a pipe, the natural length scale that you will choose is the diameter of the pipe, or if is for interest is the pressure changes, the pipe is long, maybe the length of the pipe. But those are the two choices. You're not going to choose something else. So in every problem there is some choice that you have to make. Of course, when you render the result in dimensional form, the answer must be the same. So the answer doesn't really depend on that choice. What do depend on that choice is that you're going to have parameters appearing in this equation. And if you want to analyze the system by exploiting the fact that this parameter can be small or large, then the choice of non-dimensionalization is important. That we are going to see that we are going to use this to our advantage a few times in these lectures. So in this general discussion, we're going to scale all the state variable like pressure, density, temperature with respect to the unburned state. So let's say the unburned state is P naught, rho naught, T naught, okay? And of course, when you choose this, P naught, rho naught, T naught must satisfy the equation of state, otherwise there's some inconsistency. So this is the choice that you make. So when I say we choose, so what I mean by this is that we write, let's say P tilde is going to be the dimensional quantity. So the P is the dimensionless. So we write everywhere P as P tilde over P naught. Same for all the other variables. I think I will use this notation also when I want to revert to dimensional quantity. I think I will use tilde in most of my slides. Okay, the next thing is a characteristic speed. Let's choose some velocity v naught. At the moment, we don't know what it is, but we have to specify it. Okay? We cannot, by the way, choose to characterize things with something that we don't know, because that unknown appears in the equation. So that's important to remember. Okay. We have, of course, a choice to choose the length scale as the scale of our combustor, or to look at the more smaller phenomena near the flame and to choose the diffusion length as a unit of length. Now, this ratio, d thermal, which is the thermal diffusivity, defined here, have units of centimeters square per second. If you divide it by velocity, which is centimeter per second, this has units of length. So this is related to diffusion length. I call it diffusion length. More precisely is the thermal diffusion length, because it's the thermal diffusivity, but I'm not going to be picky about those words, given the fact that all diffusivities are not very much different. But of course, you can choose to scale your problem with instead of the thermal diffusivity, the mass diffusivity, say, of the fuel. But then your equation will look a little different than the one I obtained here. Okay. Some of these trivial comments that I make are important because they often cause confusion if you don't scale things consistently. Once you have a velocity and a length scale, the time scale can be taken to be the ratio, but of course that is not necessarily unique. You may have a problem where there is a different time scale due to some boundary condition that something is oscillating, or in the frequency is a time scale, or something else, okay? So these are always at the hand of the modelers to choose the proper scales that you want. Okay, so these are the scales, and now if we take our equations and write them in dimensionless form, that's the form that they will get. Okay, the mass conservation equation doesn't change. All these symbols are going to be defined. In fact, since you have the notes in front of you, I suggest that you look at the next transparency at the same time as I am going through this equation. So what you see, the first equation doesn't change, so the mass conservation. Here is the momentum conservation. And what you see is, first of all, in front of the viscous term, there is a Prandtl number, okay? Well, those of you who are familiar with fluid mechanics usually know that there is a Reynolds number there, right? But the Reynolds number is usually based on some length scale of the problem. Here, we chose very specifically what the length scale is. And for our length scale, where's my Reynolds number? Here. So for our length scale, the reciprocal of the Prandtl number, it's exactly the Reynolds number, because if you choose the dimension, the LD, which is the diffusion length, which was, remember, lambda over rho Cp, it's not written here, but it was d thermal divided by V naught, right? So that if you put that here, then you obtain that this is exactly the Prandtl number mu Cp over lambda. So the fact that I chose the diffusion length as my length scale, then the parameter here, or the reciprocal of the Reynolds number, is the Prandtl. It's not the Reynolds number of the entire flow, it's the Reynolds number based on the, if you want, the flame thickness or the diffusion length. Okay. Another parameter that appears here is in front of the pressure. Very often in fluid dynamics, we refer the pressure to the dynamic pressure. Well, here we did not. Remember, we scaled pressure with P naught, the ambient pressure, and the density and velocity and so on with rho naught. And so the fact that there is a Mach number square here, it's because there is a P naught over rho naught, and that's the speed of sound, right? And so, and the P naught come from this P, and the rho naught come from this rho when you scale it. So what you have here is the reciprocal of the speed of sound square, m square, and that is defined here. Okay? Okay, now, oops. Now, the last one is it's the least important one in our discussion. It will come up only once or twice, but it's known as the Froude number, and this is the ratio of the inertia divided by gravity. Okay, it's defined here. Okay, the inertia is related to V naught squared divided by the length scale divided by the acceleration g, assuming that it's the only body force, of course. Okay, so this is the Froude number. Yeah.
The Prandtl number appears in the formula because you chose thermal diffusivity?
The what? I'm sorry?
Prandtl number.
Yes, because the Prandtl number appears here because I chose the diffusion length as my length scale.
Is it because you chose thermal diffusion instead of
Right.
mass diffusion?
No, it's because of thermal diffusivity. It doesn't matter mass diffusivity, they are equivalently the same. It's because thermal diffusivity, in other words, I chose the diffusion scale, which is small, and not, let's say, the scale of your flow field, okay? If you choose the scale of the flow field, then you'll have a Reynolds number based on that length.
Even if you had mass diffusion of mass, then it still would be Prandtl number, right?
It will be, well, it will be Prandtl number multiplied maybe by a ratio of viscous by a Schmidt number. Viscous, right? Because it depends on, okay, it's one of the ratio of the two diffusivities. Okay. So this is about the momentum equation. Now the species equation, since we have two species to follow, the fuel and oxidizer in general, then we have two equations, and what appears here, it's what is known as the Lewis numbers. I mentioned that before, but the Lewis number is the ratio of the thermal to mass diffusivity. So you see, if you scale with the mass diffusivity, that ratio will be different, okay? In fact, instead of having in the equation, if we, for example, scale with respect to the fuel diffusivity, then here you're going to have a 1, but then in the energy equation, you're going to have a Lewis number, okay? So this is the common way of doing it so that the equation look more or less similar to what you have seen in most cases, but not all. In fact, even that definition of Lewis number is often confusing. Chemical engineers like to define this in the opposite way. In other words, instead of thermal to mass diffusivity, they like to define it as mass to thermal diffusivity, and then they confuse you because when you talk about Lewis number less than 1, what they mean is Lewis number bigger than 1. So always when you see something that refer to this number, make sure you know what the definition is, because that can be confusing often. And a good source of that mentioned that confusion, it's written by chemical engineers actually, but doing a lot of work in combustion, is a book by Rosner, if any one of you is familiar with, Daniel Rosner from Yale. So, but he mentioned that and he clearly stated that difference. So anyway, so we came here to the these two equations, then those are the two Lewis numbers. One is related to the fuel and the other one to the oxidizer, and these are this ratio. Okay, now on the right-hand side, this is the reaction rate made dimensionless, and I will tell you later how what it looks like. In fact, it's written here, and of course there will be some parameters in front of it. But note that I ensure that there is a 1 here, and in the oxidizers there is a nu, and this is the nu I have mentioned before, which is the oxidizer to fuel stoichiometric ratio, and I think it's written down here too. Okay? Okay, so these are these two equations. Now the energy equation. The energy equation, since we use thermal diffusion or diffusion at the length scale, clearly that then diffusion will have a 1, no Lewis number, okay? And then there will be just the Mach number appear here, but also multiplied by the Prandtl number. So nothing to say in particular here. This is the gamma, the ratio of specific heat. And finally, there is a small q here, which represents the heat release parameter, okay? From now on, we are not going to use any more heat flux. We already substituted that into the equation, and so, okay, so this is the heat release parameter Q. And in this form, clearly the equation of state will be P equal to rho T, because we scaled P with P naught, rho with rho naught, T with T naught. Okay, and finally the reaction rate would have the fuel mass fraction raised to NF, the oxidizer mass fraction to NO, density to the sum of the two, right? It comes from the concentration. And there is a parameter here which is known as the Damkohler number, which I will talk about it in a minute. And then in the exponential, you have usually E over RT, right? So when you scale it, E over RT naught is this beta naught, which is the activation energy parameter. So here is the activation energy parameter. This is not what is often referred to as the Zeldovich number. I will come to that later. But this is the activation energy parameter. And here is the Damkohler number. Of course, the Damkohler number will dump in it all the things that when you scale the equation are brought to the right-hand side. Because the reaction rate also, remember, has molecular weight raised to some power, and this B and so on. So it may look a little ugly in form, but I wrote it in a way that it identifies its physical meaning. So there is the diffusion length LD divided by V naught. Let me write what LD is here so that it's clear. So LD is the thermal diffusivity, which is lambda over rho Cp divided by V naught. Okay? And so, right, I wrote that before, but just for clarity, I have it here. So this is a time, right? Have a unit of time, and that's related to the diffusion time, or in this case, to the flow time, okay? Which is due by diffusion. In the denominator, I have everything, there is a reciprocal essentially of B, and B is essentially the reaction rate constant, which is the reciprocal of time, right? And so B to the minus 1 is a time, but this is related to the chemistry, to the chemical reaction time. So the Damkohler number is essentially the ratio of flow time to reaction time. And that's, the rest here are just the details, but nothing else, okay? Okay, so these are the dimensionless parameter in this equation. I want to take one more minute to go through one more thing, and then we'll take a break. And this is the lone Mach number approximation. If you look at the equation here, and we have seen before that deflagration or flames are very slow relatively to the speed of sound. I mentioned that they propagate at a rate of 10 to 100 centimeters per second. And so clearly, And so relative to the speed of sound, which is 30,000, 34,000, the ratio, the Mach number is extremely small. It's a very small number. What this implies when you look at this equation is that if this is a very small number, then if you multiply through, everything is multiplied by a small number and you get the gradient of p is 0. Gradient of p is 0 means that p does not depend neither on x, nor on y, nor on z. So it doesn't depend spatially. It may depend on time, but not spatially. So it's nearly the pressure is nearly equilibrated immediately in the field. And this is because the speed of sound travels very fast compared to the gas. So the consequence of this is that P can be written as essentially a function of time only, plus a small perturbation of the order of the Mach number squared P hat. And when you substitute this into the momentum equation, then the only contribution to the pressure are the P hat. Now you see the gamma Mach number squared cancel. And so you have the small change in pressure that equilibrate the small change in momentum. Momentum is small because the velocities are small. And so this is the momentum equation that result. But the consequence of this is that in the equation of state, for example, only this capital P would appear, but not this pressure. In other words, that's a small perturbation, negligible. And if there is nothing that changed the pressure in time, then it will be constant. So essentially, it's the so-called quasi-isobaric relation or quasi-isobaric approximation. More generally, is the low Mach number approximation. So rho t is essentially 1 unless there are changes in pressure due to various things, which I will mention in a minute. The second thing that happened is that in this equation, because the Mach number is small, the viscous dissipation is extremely small, negligible. There is enough heating and combustion, there is enough change in temperature due to combustion that the small frictional forces don't really affect the system so much. So this is gone, and this dp dt, which was the material derivative, just replaced by just the capital P, which is the change in the pressure in time of the ambient pressure in time if it changes. If not, that's 0. So if there is, so here are the equations that we are left, is there is a change in the low Mach number approximation, and there's change in that the momentum equation now consists only of this P hat, and I removed the hat as I indicated here, I think, or here. And the equation of state is just rho t equal to P, and the work force due to the pressure is only due to the change in the ambient pressure or the global pressure. Now, P will change in time if combustion occurs in a closed system, because then the pressure increases in time. So then you have to retain this term in the equation. But or P can change in time if there are some boundary conditions that impose some changes in the global pressure. Otherwise, in a free, if you have combustion in a free space, then P, the capital P is the ambient pressure, which we have scaled it to be with P naught, so it's 1. So then we replace this by 1 and this by 0. And these are the low Mach number approximation that we'll be using. So let's take a break, and then we continue from